Now let's try to understand the metric system.
Yes, sir.
There's a metric system. I already wrote on that side of the board.
Yes,
you can just refer to that side, then we talk about it on this side. There's more before this, and there's still more after this. So I just picked this one because this is what we'll be working on this course.
Yes, sir.
Let's start by talking about the gig. Giga is like 10 to the power 9.
Yes, sir.
Do you know what does it mean? It means that there's a 1 and the 9 zeros after the 1.
Yes, sir.
It's 1, 2, 3. 1, 2, 3. 1, 2, 3. At the end you have 9 zeros. Now imagine that this is power. So we're going to write it in watts. Look how big this answer is. Can you see how big this answer is?
Yes, sir.
So sometimes maybe it won't even fit on a paper. So to make it small, we need to count the number of zeros. We already know that there are 9, wasn't it?
Yes, sir.
So it's be like 1 multiplied by 10 to the power 9 watts. But there's still another more way to make this thing smaller. This answer. You can just write 1 gigawatts. The watt, you can just leave a W like this, mustn't it?
Yes, sir.
You see how small is this as compared to this?
Yes, sir.
Yes. So it goes for the rest of the metric system.
Yes, sir.
Now let's touch milli. Milli started a small m.
Yes, sir.
Don't confuse milli with mega. Now milli is like 10 to the power minus 3. But now with the milli, okay, if you see a negative above the 10, it means now the zeros are not after 1,
Yes,
they are before 1. So we write it like this. It's 0, 0, 0, 1. Let's say amps. Amps is current, mustn't it?
Yes, sir.
Now this is your answer. You see, it's still big, so you can make it small. Now you see this one have a comma. You start there by the comma and you count 1. Okay, count 1, 2, 3. But now you started from the left going to the right, which means now it won't be kilo.
Yes, sir.
Since we started from the left going to the right, the number is negative, mustn't it?
Yes, sir.
Yes. So we're gonna write it as 1 multiplied by 10 to the power minus 3 amps. Or we can even make it smaller by writing 1 milliamps. You can just take an A. Oops. You see, it's an international standard. So now if you count okay, let me write. So now if you count from a comma to the right, the exponent is negative, ne?
Yes.
Let me just write here. But if you count from the last 0 to the left, which means you're going this direction, the exponent is positive. You see, what is an exponent? If I write a 10 to the power 3, 3 is an exponent, ne?
Yes, sir.
10 is the base, 3 is the exponent. So let's count this one and see. It's 1, 2, 3, 4, 5, 6. So we're going to put a 0 here. So this is more like 0.1 multiplied by 10 to the power?
10.
No. We just counted now. It's 1, 2, 3, 4, 5, 6. 6, ne?
Yes, sir.
Is 6 positive or negative?
Negative.
Negative 6. Where is negative 6 here? Micro. We pronounce it as micro. So we can also write it as 0.1 micro. No. Micro is not written like this. It's written like this, ne?
Yes, sir.
I'm gonna put symbols there as you go along. I don't want to overload your brain, ne?
Yes, sir.
Now let's count this one. We are going to the left. 1, 2, 3, 4, 5, 6. So this one, we write it as 1 by 10 to the power
6.
6. Where is 6 there on the board?
Mega.
Mega. Ne?
Yes, sir.
So you can write it as 1 mega. You just take this one. Unit is just 1. Deci, centi, milli, except for this one. Since the 2 m's there, they'll be confusing. So they write this one as like a U like this. That's what micro looks like. And then nano is N. You take this one. Pico is P. It's an introduction to the metric system. Ne?
Yes, sir.
If you count from the right going to the left, the exponent is positive. If you count from the comma to the right, the exponent is
Negative.
easy.
Yes, sir.
Afternoon.
Afternoon, sir.
How's everyone?
We are fine, thanks for you, sir.
You already know. Today, we will learn how to determine charge that is stored in a capacitor. Ne?
Yes, sir.
Remember, this is a capacitor. But this one is a symbol for a non-polarized capacitor. Ne?
Yes, sir.
If you draw the electrolytic capacitor, you draw it like this. Ne?
Yes, sir.
This is our positive, this is our negative. Now let's say we connect these capacitors of ours across the battery. Ne?
Yes, sir.
We're just going to assume that this is a 10 microfarad, 35 volt voltage rating, ne?
Yes.
And then you connect it across the battery. The battery is 9 volt, ne?
Yes, sir.
With a plus and a minus. So obviously the current will flow in this direction. Ne?
Yes, sir.
The current will flow in this direction. It flows inside the wire, not outside. Ne?
Yes, sir.
And charge displayed with a positive charge. The one on this side will be negatively charged. Ne?
Yes, sir.
So what will be the voltage across this capacitor? Anyone who can guess? Is it going to be 35 volt or is it going to be 9 volt?
9 volt.
9 volt. 100% correct. Let's assume that we have a bucket, ne?
Yes, sir.
Like this. This bucket can carry 5 liters of water, ne?
Yes, sir.
But you only pour 2 liters. How much water will be in the bucket?
5 liters.
No,
2.
2 liters. You'll only have 2 liters of water, ne?
Yes,
It can carry 5 liters maximum, ne? But you only pour 2 liters. So you only get 2 liters inside the bucket, ne? The same applies with the capacitor. This capacitor can handle up to 35 volt. Does it make sense?
Yes,
But you only supply it with 9 volt. So it will charge up to 9 volt. Then it will stop right there. Does it make sense?
Yes, sir.
Yes. So now we need to calculate how much charge we will have in this capacitor, ne?
Yes, sir.
After it is fully charged. So we have charge is given letter Q, ne?
Yes, sir.
Is equal to C for capacitance multiplied by voltage. Then capacitance is this one, must it?
Yes, sir.
It is 10 multiplied by 10. Now what will be the exponent? You see the prefix, how it looks like?
Yes, sir.
It looks like a micro. Show me micro there on the board. What is the power of micro?
6.
It's -6, -6, ne?
Yes, sir.
Multiplied by the voltage, which is the supply voltage that filled up the capacitor, ne?
Yes, sir.
So 9 multiplied by 10, it is 90 multiplied by 10 to the power -6. So the charge that's going to be stored inside the capacitor is 90 microcoulomb. The unit for charge is coulomb, ne?
Yes, sir.
Or the synonym for charge is coulomb. See how easy it is?
Yes.
Don't assume that it's small. There are still big capacitors that can store more than this, ne?
Yes, sir.
And then the bigger the capacitor, the greater the charge, and the more dangerous it becomes, ne?
Yes, sir.
So now let's determine the energy across this capacitor. The energy is E is equal to half multiplied by charge multiplied by capacitance multiplied by square of the voltage, ne? So you're going to have 1/2 multiplied by 10 to the exponent -6 multiplied by 9 squared. 9 squared is 81, ne?
Yes, sir.
81 multiplied by 10, 810. And then we divide it by 2. You see. You say I'm lying. You have a 9 squared, which is 81 multiplied by 10 to the power -6, divided by 2. It gives us 405. 405 multiplied by 10 to the power -6. The synonym for energy is joule, ne?
Yes, sir.
Don't worry about this, I'll teach you later. So, which letter do we put here? It is 10 to the power -6, or 10 to the exponent -6. Look there by the metric system. Micro. Now we have 405 microjoules. That's the amount of energy that is stored in this capacitor. Does it make sense?
Yes, sir.
Nah, it makes sense to me too, né?
Yes, sir.
Now, have you ever wondered why is that the bigger the capacitor in size, the bigger the capacitor, the greater the capacitance? Let's say we have a capacitor this big. With a stripe here, né? The short leg and the long leg. And then you have another one. This small. With a stripe here. You'll find that this one is 2.2 microfarad. But this one is 100 microfarad. Why is this one is 100 microfarad and this one is 2.2 microfarad? Yes.
Because it's big.
Because it's big. Okay, let's check why is it like that. Remember most that inside the capacitor there are two plates, ne?
Yes, sir.
Oops.
Yes, sir.
Thank you. We have two plates inside, must ne?
Yes, sir.
So these plates, they help us determine the value of the capacitance, ne?
Yes, sir.
This one. So let's assume that the size of this plate, this one, is it's not that straight, ne? Let's just assume it is 10 meters and 10 meters because we calculate in meters, ne?
Yes, sir.
and the distance between the two is like 2 meters, ne?
Yes, sir.
So let's try and calculate the capacitance of this capacitor. The formula is C for capacitance is equal to permeability, the material inside, how much does it allow the electromagnetic field to cross over. We call it a permeability, ne?
Yes, sir.
And then we multiply it by the area of this plate, ne? And then we divide it by the distance between the two, ne? This is equal to a distance. You see?
Yes,
Now the permeability is 8.85, ne? The area, we say 10 times 10 to get the area. 10 times 10 is equal to 100 divided by 2. Let's leave it like that. 8.8 multiplied by 100, 8.85. No, it's not just 8.85, ne? I made a mistake. Multiplied by 10 to the power minus 12 multiplied by 100. That's how it's supposed to be, ne?
Yes, sir.
Sorry for that. 8.85 exponent 12 negative multiplied by 100 all divided by 2. Now we get 442.5 multiplied by 10 to the power minus 12. What is the unit for capacitor? It's farad, ne?
Yes, sir.
See, it's farad. But now the exponent for 10 is minus 12. What is minus 12 on the board? Pico. So we say it's 442.5 pico farad. Yeah.
Yes, sir.
Now let's keep the distance the same and just divide these two numbers by 2, ne? So we'll have 5. You see now that the plate is smaller than before.
Yes,
Let's calculate the capacitance and see the difference, ne? The formula is still the same. The permeability is still the same. 8.85 multiplied by 10 to the minus 12 multiplied by 5 multiplied by 5 is 25. All divided by 2 because you keep the distance the same, ne?
Yes, sir.
Let me use my machine. 8.85 to the exponent 12 negative multiplied by 25 all divided by 2, and the answer is 110.63 times 10 to the power minus 12 farad. How do we minimize this? Minus 12 is 110.63 pico farad. You see now that the smaller the plate, the smaller the answer. The bigger the plates, the bigger the capacitance, ne?
Yes, sir.
That is why big capacitors, they have big capacitance value, and small capacitors, they have a small capacitance value. Do you want to see that practical? Let's go to the workbench. Okay, now I have two different size of plates, ne, that will resemble a capacitor. So you'll see that the bigger the plates, the bigger the capacitance. This one is 50 millimeters, it's 50 by 50 millimeters. Let's see how much capacitance we'll get. We use a piece of paper as a dielectric material, ne?
Yes, sir.
And then put this plate on top. Now how much capacitance we getting?
0.032
Nanofarad. Ne?
Yes, sir.
Now let's check the big one. 0.032 nanofarad. Now let's check the big. Now here I have a 100 by 100 millimeter plate, ne?
Yes, sir.
Same with the piece of paper with dielectric, ne?
Yes, sir.
Now let's see how much capacitance we catch. You see this one is almost double that one, ne?
Yes, sir.
That one was 0.032 nanofarad, ne?
Yes, sir.
Let's see this one. This one is 0.080 nanofarad, ne?
Yes, sir.
Did you see that the bigger the plate, the greater the capacitance?
Yes, sir.
So I was not lying, ne?
Yes, sir.
Let's check these ones here. See, this one is bigger. It's 2200 microfarad, ne?
Yes, sir.
The biggest one. Now let's check this one. This one is 1000 microfarad with 35 volt, and the small one is 10 microfarad, ne?
Yes, sir.
Now you know why they differ in size, ne?
Yes, sir.
Yes.